Picture this: a world without electricity, without telescopes, without any of the tools we take for granted today. Yet, under the vast expanse of the night sky, ancient civilizations gazed up at the same stars, the same swirling auroras, the same fiery comets that streak across the heavens, and they felt something profound. Awe, wonder, an unshakable need to make sense of it all. Long before modern science could explain the mysteries of the natural world, our ancestors were already chronicling these phenomena in ways that would shape their cultures, their religions, and even their survival. From the dazzling dance of the northern lights to the sudden darkness of a solar eclipse, these events weren't just celestial occurrences. They were messages, omens, stories waiting to be told. Think about how it must have felt to witness a total eclipse thousands of years ago. The sun, the very source of life, vanishing without warning, the temperature dropping. Animals falling silent. For early societies, this wasn't just a scientific curiosity. It was a moment of sheer terror or divine intervention. And so, they did what humans have always done. They recorded it. They carved it into stone, painted it on cave walls, wove it into myths passed down through generations. These weren't just observations. They were attempts to understand their place in the universe. The Babylonians tracked planetary movements with astonishing precision. The Maya built entire calendars around celestial cycles. The Norse saw the aurora borealis as the armor of their gods, shimmering in battle. Every culture, in its own way, turned the unknown into something meaningful. What's truly remarkable is how much of their knowledge still echoes today. Those early star charts, they laid the groundwork for modern astronomy. Those myths about eclipses and comets, they reveal universal human fears and hopes. This video is a journey back to those moments of discovery, to the ingenious methods ancient societies used to document the wonders of the natural world. We'll explore how they turned chaos into order, mystery into meaning, and how their legacy lives on in the science and stories we tell today. By the time we're done, you'll never look at the night sky or human history the same way again. So let's step into their world and see the heavens through their eyes. Before the invention of writing, before even the first symbols were etched into clay or stone, there was something far more powerful: the human voice. For thousands of years, oral traditions carried the weight of human knowledge, especially when it came to the mysteries of the natural world. Imagine sitting around a fire, the night sky stretching endlessly above, as an elder recounted the story of how the sun once disappeared from the sky, a tale passed down for generations to explain a solar eclipse. These weren't just stories, they were living records meticulously preserved through rhythm, repetition, and ritual. Take the Aboriginal peoples of Australia, for example. Their Dreamtime stories didn't just describe the land, they explained its very creation, tying celestial events to the formation of mountains, rivers, and deserts. A meteor streaking across the night sky might become the fiery spear of an ancestral spirit, while the phases of the moon could mark the passage of sacred time. These narratives did more than entertain. They encoded vital knowledge about seasonal changes, animal migrations, and even navigation. The rhythmic structure of oral storytelling made it easier to remember, ensuring that crucial information survived centuries without a single written word. But oral traditions weren't just about preservation, they were about meaning. A sudden comet or an unexpected eclipse wasn't just a scientific event, it was a message, a warning, or a sign from the gods. The Norse believed the northern lights were the reflections of Valkyrie armor, while the Maori of New Zealand saw them as the torches of ancestors guiding the living. These interpretations gave people a way to cope with the unpredictable, transforming fear into folklore, wonder into wisdom. What's astonishing is how accurate these oral records could be. Researchers have found that some indigenous star knowledge, passed down purely through speech and song, aligns perfectly with modern astronomical observations. The stories weren't just myths, they were a sophisticated way of observing, recording, and teaching. So the next time you hear an ancient tale about the heavens, remember, you're not just listening to a story. You're hearing the echoes of humanity's first scientists, poets, and philosophers, all trying to make sense of the vast, beautiful mystery above us. Long before paper or parchment existed, our ancestors turned to the most permanent canvas they could find, the very walls of caves and cliffs. Scattered across the globe, from the shadowy chambers of Lascaux to the sun-baked cliffs of Bimbetka, these rock surfaces became humanity's first astronomical records. Picture an artist tens of thousands of years ago, grinding minerals into pigment by firelight, carefully tracing the arc of a comet or the explosive burst of a supernova. These weren't idle doodles, they were deliberate, awe-struck attempts to capture the extraordinary. Take the famous Lascaux cave paintings in France. Among the vivid depictions of bison and horses, researchers have identified a series of dots and arcs that may represent the Pleiades star cluster, a celestial landmark still used for navigation today. Even more striking, a bullseye symbol in the same cave could depict the catastrophic eruption of a supernova, its sudden brilliance immortalized in ochre and charcoal. Halfway across the world, in India's Bhimbetka rock shelters, ancient artists painted what appear to be solar disks with radiating lines, possible records of eclipses or halos around the sun. What's fascinating is how these images blend science and spirituality. A swirling pattern might represent both a tornado and a deity's wrath. A cluster of stars could serve as both a seasonal calendar and a sacred map to the afterlife. For early societies, the boundary between observation and mythology didn't exist. A comet wasn't just a ball of ice and dust, it was a fiery omen, a herald of change. By painting these events, they gave them meaning, turning chaos into something tangible, something they could revisit and reinterpret with each generation. The sheer endurance of these artworks is a testament to their importance. Unlike fragile scrolls or carvings that erode, rock art endured millennia of wind, rain, and human history. Today, they're like prehistoric postcards, whispering across time about the wonders our ancestors witnessed. And here's the remarkable part. Modern astronomers have cross-referenced some of these symbols with known celestial events. That bull's eye in Lascaux, it aligns with a supernova that would have blazed in the sky around 16,600 years ago, visible even in daylight for weeks. These caves aren't just galleries, they're humanity's first observatories, where art and science were born under the same starry sky. Now consider the sheer scale of human ambition etched into stone across the ancient world. Towering megaliths arranged with impossible precision, standing silent for thousands of years. These weren't just monuments, they were celestial calendars, engineered to capture the exact moment sunlight pierced a hidden chamber or cast shadows along sacred pathways. Take Newgrange in Ireland, a massive tomb older than the pyramids. Every winter solstice at dawn, a narrow beam of light creeps through a perfectly aligned opening, flooding the inner chamber with golden light for exactly 17 minutes. This wasn't accidental architecture. It was a deliberate, breathtaking act of aligning human creation with cosmic rhythm. The builders of Stonehenge took this precision even further. Those iconic stones, they frame the summer solstice sunrise so perfectly that modern crowds still gather to witness the phenomenon each year. But here's what's truly mind-blowing. The structure also tracks lunar cycles, with certain alignments matching the moon's extreme positions every 18.6 years. How did Neolithic people, without written records or advanced tools, calculate such complex patterns? The answer might lie in generations of patient observation, passed down through oral traditions we can only imagine. Then there's the Great Pyramid of Giza, where astronomy and architecture merge on a staggering scale. Its air shafts align with stars like Sirius and Orion's belt, constellations tied to Egyptian myths of rebirth. The pyramid's sides are so precisely oriented to cardinal directions that modern engineers still debate how such accuracy was achieved. But perhaps the most revealing detail is this: the entire Giza plateau mirrors the stars of Orion's belt, with the pyramids positioned just as the stars would have appeared in 10,500 BC. This wasn't just symbolism, it was a sacred map permanently anchoring celestial patterns to the earth. What these structures share is a profound understanding of cyclical time. For agricultural societies, predicting solstices meant knowing when to plant or harvest. For spiritual leaders, celestial alignments marked sacred moments to commune with gods. The stones themselves became eternal witnesses, turning abstract astronomical knowledge into something tangible, something you could touch, walk between, or watch illuminate with the turning of the seasons. Today, as lasers scan these sites and reveal new alignments, we're left with awe for the minds that saw the sky not as a mystery, but as a blueprint. While oral traditions and rock art captured the heavens in fleeting words and pigments, another revolution was unfolding in the Fertile Crescent, one that would change how humanity recorded the cosmos forever. Pressed into soft clay with wedge-shaped reeds, the Sumerians and Babylonians created something astonishing: the world's first written astronomical records. These cuneiform tablets didn't just describe the stars, they quantified them, tracking planetary movements with a precision that still impresses modern scientists. Take the Venus tablet of Amasajuka, a fragile clay rectangle from around 1600 BCE. Its precise notations of Venus's appearances and disappearances over 21 years reveal an almost obsessive attention to celestial patterns. But here's what's truly fascinating: these weren't cold, clinical observations. Every eclipse, every planetary alignment was interpreted as a divine message, a cosmic conversation between gods and mortals. The Babylonians saw omens in everything. A red halo around the moon might predict war. Jupiter's position could foretell the fate of kings. Their astronomers, often temple scribes, developed complex systems to correlate celestial events with earthly outcomes, what we'd now call early astrology. Yet beneath the mystical interpretations lay razor-sharp mathematics. By the 7th century BCE, they'd calculated the length of a lunar month within 4 seconds of modern measurements. Their mull-a-pin tablets, essentially ancient star catalogues, mapped constellations and tracked planetary motions with remarkable accuracy. This blend of meticulous record-keeping and symbolic meaning created a unique bridge between spirituality and science, one where the movement of Venus wasn't just a planetary orbit, but the footsteps of the goddess Ishtar walking across the sky. What sets these tablets apart is their sheer longevity. Unlike oral traditions that could shift with each telling, or cave paintings vulnerable to erosion, baked clay preserved knowledge across millennia. When archaeologists unearthed the library of Ashurbanipal in the 19th century, they found tens of thousands of these tablets, a time capsule of Bronze Age astronomy. Modern researchers can still trace finger grooves in the clay, following the same calculations scribes made over 3,000 years ago. That continuity allowed Babylonian eclipse records to help contemporary scientists measure changes in Earth's rotation, proving these ancient astronomers weren't just stargazers, but pioneers whose work echoes in observatories today. Perhaps most remarkable is how these tablets reveal the birth of systematic science. The Babylonians didn't just record one-off events. They identified patterns, developed prediction methods, and even corrected earlier errors, hallmarks of the scientific method. Their Venus observations followed strict formats: date, position, duration, all standardized across generations of scribes. This wasn't storytelling or art, it was data collection on an unprecedented scale, turning the chaotic dance of planets into something predictable, even manageable. So the next time you check a weather app or read a horoscope, remember, you're participating in a tradition that began when someone pressed a reed into wet clay beneath the same stars we see tonight. Deep in the rainforests of Mesoamerica, where howler monkeys echoed through the canopy, the Maya were quietly revolutionizing humanity's understanding of time itself. Their bark paper codices, folded like delicate fans, contained mathematical secrets that could predict celestial events with eerie accuracy centuries before telescopes existed. The Dresden Codex, one of only 4 surviving Maya books, isn't just a relic, it's a masterpiece of cosmic computation. Within its weathered pages, red and black glyphs trace the dance of Venus with such precision that modern astronomers found its calculations for the planet's cycles were off by just 2 hours per 500 years. Imagine crafting that level of accuracy using nothing but observational records passed down through generations. But this wasn't cold mathematics divorced from culture. For the Maya, time was sacred, a living force woven into every aspect of existence. Their famous long-count calendar didn't just measure days, it synchronized solar years, sacred cycles, and even the human heartbeat with celestial rhythms. Priests used these calculations to determine when to plant crops, when to wage war, or when to conduct bloodletting rituals to commune with the gods. A solar eclipse wasn't merely an astronomical event. It was a moment when the sun serpent devoured the sky, demanding offerings to restore balance. The Dresden Codex's eclipse tables, spanning 33 pages, weren't academic exercises. They were survival guides for a society that believed the cosmos demanded participation. What's truly staggering is the sheer scale of their temporal vision. While European scholars still debated whether Earth was round, Maya astronomers had already calculated the length of a solar year to within minutes of today's measurements. Their lunar cycle records corrected themselves every 440 days to maintain accuracy, and their Venus tables spanned thousands of years. This long-term thinking reveals something profound. The Maya saw time as a vast, interconnected web where past and future eclipses were threads in the same grand design. The tragedy of the Spanish conquest left most of these codices burning in bonfires, branded as heresy. Yet the fragments that survived, like the Dresden Codex's hauntingly accurate eclipse predictions, whisper of a civilization that didn't just watch the stars but conversed with them. Today, as archaeologists decode more glyphs, we're realizing the Maya didn't merely record time, they mastered it, turning the unfathomable vastness of the cosmos into something intimate, something human. Their legacy challenges us to reconsider what primitive really means when their calculations still hold up against our satellites and supercomputers. While Babylonian astronomers pressed celestial knowledge into clay and the Maya folded time into bark paper codices halfway across the world, Chinese stargazers were perfecting another revolutionary method, the art of mapping the heavens with bureaucratic precision. Picture the imperial observatories of ancient China, where scholars perched on towering platforms, their ink brushes hovering over silk scrolls as they logged every anomaly in the night sky. These weren't casual notes, they were state-mandated records tied to the very survival of dynasties. When a guest star, what we now call a supernova, blazed unexpectedly in the constellation Taurus in 1054, Chinese astronomers documented its position, brightness, and duration with such exactness that modern astrophysicists later identified it as the Crab Nebula's violent birth. The Dunhuang Star Atlas, discovered sealed in a Buddhist cave library, reveals just how sophisticated their celestial cartography had become by the Tang dynasty. Painted on paper that's over 1,300 years old, it's the oldest complete star map in existence, charting more than 1,300 stars with startling accuracy. What's extraordinary is how it merges science and mythology. Constellations are drawn as celestial bureaucrats, each star a dot connected by thin red lines to form the outlines of mythical figures governing different sky sectors. This wasn't just navigation, it was a cosmic mirror of imperial China's own ordered hierarchy, where heaven and earth reflected one another. But the true brilliance of Chinese astronomy lay in its longevity. For over 2,000 years, court astronomers maintained unbroken records of comets, sunspots, and supernova. When Halley's comet streaked across the sky in 240 BC, they noted its path and timing, a record so precise it helps calibrate the comet's orbit today. Solar eclipses were logged with similar care, not just as celestial events but as omens requiring imperial response. Emperors would fast, issue pardons, or even demote officials to appease the heavens. In one striking example, two astronomers named HSI and Ho were allegedly executed for failing to predict an eclipse in 2135 BC, a grim reminder of how seriously these observations were taken. What set China apart was its systematic approach. Unlike cultures that viewed celestial phenomena as isolated wonders, the Chinese treated them as data points in a vast, interconnected system. Their records often included atmospheric conditions, earthquake correlations, and even market prices, recognizing cosmic events as threads woven into the fabric of daily life. Modern researchers still scour these annals, using descriptions of broom stars, comets, and sparkling stars, nova, to date stellar explosions and track cosmic debris. It's a testament to their rigor that when NASA needed historical data on supernova, they turned first to the meticulous scrolls of Song dynasty astronomers. Perhaps most poignant is how these records reveal a civilization that saw no divide between science and statecraft. A comet's tail wasn't just ice vaporizing in sunlight, it was a heavenly edict, a warning of droughts or rebellions. By binding astronomy to governance, the Chinese created a self-correcting system where accuracy wasn't just scholarly, it was a matter of dynastic survival. Today, as radio telescopes probe remnants of those ancient supernova, we're not just studying stellar debris, we're deciphering humanity's longest conversation with the cosmos. While ancient cultures often saw natural phenomena as messages from the gods, the Greeks and Romans began asking a radical new question: what if the world operated by its own rules? Aristotle, walking the shores of Lesbos in the 4th century BC, didn't just marvel at seashells embedded in rock. He deduced that land must have once been underwater. When he studied rainbows, he didn't attribute them to Iris, the messenger goddess he hypothesized about light refracting through water droplets. This was a seismic shift. Nature wasn't just something to worship or fear, it was a puzzle to solve. His Meteorologica, though flawed by today's standards, systematically explained everything from comets to earthquakes as natural processes, not divine whims. Then there was Ptolemy, whose Almagest became the astronomical Bible for over 1,000 years. Working in Alexandria's legendary library, he didn't just map stars, he calculated. His tables predicted planetary motions with such precision that navigators used them well into the Renaissance. The genius of his work lay in its blend of observation and mathematics. Ptolemy didn't claim the planets moved in perfect circles because the gods demanded symmetry. He crafted complex models like epicycles to match what he actually saw in the night sky. It wasn't perfect. His Earth-centered universe was later overturned, but the method itself was revolutionary. Collect data, test theories, refine. Roman scholars took this further by weaving fieldwork into their texts. Pliny the Elder's natural history reads like an ancient Wikipedia, crammed with everything from volcanic eruptions to the habits of dolphins. When Vesuvius buried Pompeii, his nephew Pliny the Younger documented the eruption stages with chilling detail: the rising ash column, the sheets of fire, the suffocating pumice rain. These weren't just dramatic accounts, they were early attempts at disaster science, noting how winds carried ash or how earthquakes preceded eruptions. Yet even in their empiricism, the wonder remained. Pliny marveled at rainbows as the sky touching the earth, and Ptolemy saw the cosmos as a living, divine thing. What set these texts apart was their dual legacy. They pushed toward rational explanations while preserving the awe that fuels discovery. Aristotle's errors, like claiming heavier objects fall faster, don't diminish his breakthrough, the idea that nature follows consistent laws we can uncover. Ptolemy's flawed solar system still taught medieval astronomers how to measure the heavens, and Pliny's encyclopedic curiosity, though sometimes crediting unicorns or magic stones, showed how observation could build a framework for understanding the world. Their work became a bridge between myth and microscope, between stargazing and satellites, proving that seeking answers doesn't have to extinguish wonder. If anything, it deepens it. Now imagine standing on the deck of a canoe no wider than your outstretched arms, with nothing but open ocean stretching to every horizon. No compass, no maps, just the swell of waves beneath you and a sky ablaze with stars. This was the reality for Polynesian voyagers who crossed thousands of miles of the Pacific using knowledge so precise it feels like magic. They didn't just glance at the stars, they memorized the rising and setting points of hundreds of constellations, using them as celestial highways, the star cluster we call Orion's belt. To them, it was Tortoru, a trio of hooks that signaled the best season for planting breadfruit. The Southern Cross became T-Punga, the anchor that held the sky in place. But their genius didn't stop there. They read ocean swells like road signs, detecting distant islands by how waves reflected off unseen shores. They watched the flight patterns of birds certain species would only fly out to sea at dawn and return at dusk, revealing land just over the horizon. This wasn't just navigation, it was a living dialogue with the natural world. The Maori of New Zealand carried this same reverence into their star lore, but with a profound twist. For them, constellations weren't just guides, they were ancestors. The Pleiades, known as Matariki, marked the Maori New Year when these celestial figures were said to weep for the dead, their tears fertilizing the earth for new crops. Each star held a name, a story, a connection to Wakapapa, the genealogical threads linking people to the land and sky. When they chanted navigational prayers, they weren't just reciting directions, they were calling to family. This fusion of astronomy and identity meant the night sky became a mirror of human experience, where every celestial event carried emotional weight. A shooting star wasn't just debris burning up, it was the spirit of a loved one passing into the next world. Meanwhile, on the Great Plains of North America, the Lakota people synchronized their most sacred ceremony with the cosmos. The sun dance, a 4-day ritual of prayer and endurance, was timed to the summer solstice when the sun stood still in the sky. They'd mark the exact moment by driving a sacred pole into the earth, aligning it so the shadow disappeared at noon. but their celestial knowledge went far deeper. They tracked the movement of the Witch-Happy-Oangilla, the star that does not move, what we call Polaris, and used it to orient their medicine wheel stone structures that mapped solstice sunrises and lunar cycles. Unlike Western astronomers who prized detachment, the Lakota saw celestial observation as inseparable from spirituality. To study the stars was to participate in the great hoop of life, where sky and earth were bound together in endless exchange. What unites these traditions is their refusal to separate knowledge from meaning. Polynesian navigators didn't just memorize star positions, they understood them as part of an oceanic ecosystem. Maori star lore wasn't cold calculation, it was memory etched in light. And for the Lakota, the sun wasn't merely a celestial body, it was Wai, the life-giver, who demanded gratitude. These weren't primitive beliefs overshadowed by modern science. They were sophisticated systems that recognized what we're only now rediscovering, that the universe isn't just something to observe. It's something to belong to. As we peer through telescopes and scan satellite data, their legacy reminds us that the stars have always been more than distant suns. They're the compass, the calendar, and the kin our ancestors knew them to be. In the quiet scriptoria of medieval monasteries, where candlelight flickered against cold stone walls, monks bent over parchment with quills in hand, documenting something far grander than religious texts. They were chronicling the heavens. The Anglo-Saxon Chronicle, a masterpiece of early medieval record-keeping, didn't just track kings and battles, it noted celestial wonders with meticulous care. When a long-haired star, what we now know as Halley's Comet, streaked across the sky in 1066, the scribes didn't dismiss it as a mere spectacle. They recognized its significance, linking it to the Norman conquest later that same year. To them, the cosmos wasn't separate from earthly events. It was a divine chalkboard where God wrote warnings and prophecies. But these monks weren't just passive observers. Their illuminated manuscripts blended art and science in ways that still take our breath away. Take the Annals of Ulster, where an entry for the year 1085 describes a blood-red aurora so vivid it seemed as if the sky itself were aflame. The description isn't just poetic. Modern researchers have used it to reconstruct historical solar activity, proving these records weren't allegories but precise accounts. Even eclipses, often interpreted as omens of doom, were logged with startling accuracy. The Chronicle of Worcester records the total solar eclipse of 1133 in such detail that astronomers can pinpoint the exact path of totality across medieval England. What's fascinating is how these records reveal unexpected connections across continents. While Chinese astronomers famously documented the supernova of 1054, European monks also caught glimpses of the same cosmic explosion. A marginal note in the Edwine Psalter from Canterbury describes a new star shining brighter than Venus, likely the same stellar cataclysm that created the Crab Nebula. Even more remarkably, these scattered accounts hint at a silent network of observations spanning Christendom, the Islamic world, and beyond. Arab scholars like Ibn Sina wrote about the supernova's fading glow, while Armenian chroniclers noted its position near Taurus. Though separated by geography and faith, they were united by the same celestial event, each culture interpreting it through their own lens of belief. The true legacy of these monastic records lies in their dual purpose. They served as both spiritual guides and scientific datasets, proving that faith and observation weren't enemies but partners. When Benedictine monks in Germany tracked the cycles of Venus, they weren't challenging church doctrine, they were seeking divine order in the motion of planets. This delicate balance allowed astronomical knowledge to survive the so-called Dark Ages, preserved in the margins of psalters and the footnotes of chronicles. Today, as historians and astrophysicists scour these manuscripts for clues about past supernova or solar storms, we're not just recovering data, we're rediscovering a time when the heavens were a living text, and every monk with a quill was a scribe of the stars. While Europe navigated the so-called Dark Ages, a brilliant light burned in the Islamic world, one that would keep the torch of astronomy alive. In bustling cities from Baghdad to Samarkand, scholars like al-Biruni weren't just preserving Greek knowledge, they were revolutionizing it. Picture this: al-Biruni, an 11th century polymath, calculating the Earth's circumference with a margin of error less than 1%, using little more than trigonometry and a mountain in India. His methods weren't just innovative, they revealed a fundamental shift in how celestial knowledge was gathered. No longer content with inherited wisdom, these scholars tested, challenged, and refined every assumption. Then there was al-Sufi, whose Book of Fixed Stars transformed how humanity saw the night sky. Working in 10th century Persia, he didn't just copy Ptolemy's star catalogue, he corrected it. With painstaking precision, he noted discrepancies in star positions, described the Andromeda galaxy as a small cloud, the first recorded observation of another galaxy, and even depicted constellations as they appeared both from Earth and as if viewed from outside the celestial sphere. This wasn't just astronomy, it was cosmic cartography of breathtaking imagination. His work became so essential that sailors and scientists relied on it for centuries, bridging the gap between ancient stargazers and Renaissance explorers. But the crown jewel of Islamic astronomy emerged in 15th century Samarkand, where Ulugh Beg built an observatory unlike anything the world had seen. His Zij table's colossal star catalogues mapped over 1,000 stars with positional accuracy unmatched until the invention of the telescope. What made these records extraordinary wasn't just their precision, but their global reach. Combining Persian, Indian, and Greek methods with original observations, Ulugh Beg's team used a gargantuan meridian arc, a sextant the size of a 3-story building, to track celestial movements with razor-thin margins of error. Their calculation of the solar year, off by just 25 seconds, the true genius of these scholars lay in their refusal to see knowledge as static. Arabic treatises overflow with marginal notes, corrections, debates, and new hypotheses scribbled by generations of astronomers. When they translated Greek texts, they didn't merely copy, they annotated, questioned, and expanded. A 9th century text like al-Khwarizmi's Zij al-Sindhine didn't just parrot Indian astronomy, it adapted their sign functions into tools for predicting planetary positions. This culture of critical inquiry created an unbroken chain of discovery, ensuring that when Europe reawakened to science during the Renaissance, the foundational work of the Islamic world was waiting, not as relics, but as living, breathing blueprints for the future. Perhaps most remarkably, these astronomers saw no conflict between faith and reason. Observatories rose beside mosques, calculations of prayer times doubled as celestial studies. In al-Biruni's writings, mathematical proofs sit alongside meditations on divine harmony, revealing a worldview where studying the heavens was the highest form of worship. Today, as we peer into deep space with orbiting telescopes, we're building on the legacy of scholars who proved that human curiosity knows no borders and that the stars belong to everyone. High in the Andes, where thin air makes the stars blaze brighter, the Inca Empire crafted a language unlike any other, not with ink or stone, but with knots. Their quippers, intricate arrays of colored cords dangling from a central strand, looked deceptively simple at first glance. Yet these twisted threads held the secrets of an empire that spanned mountains and jungles without ever developing a written script. Each knot's position, color, and even the direction of its twist encoded information, tax records, census data, and perhaps just maybe the movements of the heavens. Imagine a priest astronomer high at Machu Picchu, fingers flying over camelid fiber cords as he recorded the winter solstice sunrise creeping along the stone Intihuatana, the hitching post of the sun. Was he creating a quipu to mark the event for future generations? The tantalizing possibility lingers like morning mist over the ruins. Recent studies reveal just how sophisticated these knotted records could be. Some quipus display repeating numerical patterns that align suspiciously well with lunar cycles, 29 or 30 knots in sequence, matching the days between full moons. Others show clusters of 10, possibly representing the Inca decimal calendar's 10-day weeks. The colors themselves might hold celestial meaning: white for the moon, red for the sun, gold for Venus as the morning star. But here's where it gets truly fascinating. At the Temple of the Sun in Cusco, Spanish chroniclers described quipus tracking eclipse cycles. One account even mentions a black quipu, used specifically for astronomical events, though tragically, not a single example survives today. What sets the quipu apart is its sheer physicality. Unlike flat scrolls or tablets, these were three-dimensional records you could feel in your hands. A trained quipukamayok keeper of the knots didn't just read them, they performed them, running fingers along the cords like a harpist plucking strings to unlock their stories. This tactile dimension suggests something profound. For the Inca, time and knowledge weren't abstract concepts. They were woven into the very fabric of daily life, as tangible as the ropes that bridged their mountain passes. The quipu didn't just record data. It embodied the interconnectedness they saw in the universe, where celestial events and earthly affairs were threads in the same cosmic tapestry. The tragedy of the Spanish conquest left most quipus burned as pagan artifacts, their secrets fraying into oblivion. But modern researchers are piecing together fragments of this lost system, using everything from mathematical analysis to comparisons with contemporary Andean weaving traditions. Some scholars even suspect certain quipus functioned as mnemonic devices for oral astronomical poetry, knots prompting recitations of celestial myths now silenced by time. As laser scans reveal subtle wear patterns on ancient cords, we're glimpsing a civilization that measured the cosmos not with telescopes or parchment, but with fiber and memory. In their knotted threads, the Inca may have left us not just records, but a radical reminder: there are infinite ways to speak to the stars. Far north, where winter winds howl and the sea freezes solid, Norse sailors whispered tales of the night sky coming alive, not with stars but with shimmering veils of green and red. To them, the auroras weren't just lights. They were the armor of Valkyries, celestial warrior women who carried fallen heroes to Odin's hall. The King's Mirror, a 13th century Norwegian text, captures this blend of awe and practicality. Written as a father's advice to his son, it describes the Arctic's midnight sun with startling clarity. The orb of the sun does not disappear, but rolls along the horizon like a wheel. But it doesn't stop at poetry. The text offers survival tips for polar travelers, warning that winter darkness could last so long, men lose count of days. Here, mythology and meteorology weren't at odds. They were two sides of the same ice-covered coin. What makes these accounts extraordinary is their grounded detail beneath the mythic veneer. When sagas speak of the sky fires, they note how the lights often appeared before storms, an observation modern science confirms, as auroras intensify during solar activity that also disrupts weather. The King's Mirror even documents atmospheric refraction, explaining why the sun sometimes appears flattened at the horizon, as if pressed by a giant's hand. These weren't just stories, they were field guides disguised as folklore, teaching generations how to navigate a world where nature defied logic. A sailor who knew the auroras signaled coming storms could reef his sails in time, while understanding the midnight sun's rhythms meant knowing when to hunt migratory birds or when sea ice would crack. The Norse didn't merely endure their environment, they chronicled it with a poet's eye and a scientist's precision. Take their descriptions of the sun dogs, phantom suns that flank the real one in icy skies. Modern meteorologists recognize these as parhelia, caused by light bending through ice crystals, but the Norse saw them as Odin's omens. Yet even in myth, they nailed the physics. One saga describes the false suns, moving as the true sun moves, capturing how these illusions track with the solar position. This duality reveals a culture that refused to separate knowledge from wonder, where every shimmer of light held both practical meaning and sacred significance. Perhaps most striking is how these records transcend time. When researchers compared Norse descriptions of a blood-red aurora in 1237 with ice core samples from Greenland, they found evidence of a massive solar storm, the same event that likely inspired tales of Valkyries bathing the sky in battle light. Today, as satellites monitor solar flares, we're essentially continuing what Viking storytellers began, decoding the dialogue between Earth and sky. Their legacy reminds us that the coldest, harshest places on Earth often inspire the warmest, most human stories where science and saga aren't rivals, but partners in making sense of the dazzling, unpredictable heavens. In the scorching heat of Mali's Bandiagara escarpment, the Dogon people have guarded celestial secrets that defy easy explanation. For generations, their oral traditions spoke of a tiny, dense companion star orbiting Sirius, the brightest star in our night sky. What's astonishing is that this invisible star, now called Sirius B, wasn't discovered by Western astronomers until the 19th century with powerful telescopes. Yet Dogon elders described it centuries earlier with unsettling precision, a heavy, white seed of the universe that took 50 years to orbit Sirius. They even knew its elliptical path, a detail modern astronomy confirmed only recently. How did a culture without optical instruments grasp such an elusive cosmic truth? Some speculate contact with ancient Egyptian astronomers, whose hieroglyphs also hint at Sirius worship. Others suggest meticulous observation, perhaps noting subtle wobbles in Sirius's position over lifetimes of sky watching. Whatever the source, the Dogon's knowledge shatters assumptions about what pre-telescope societies could comprehend. 1,000 miles southeast, the towering stone walls of Great Zimbabwe whisper of another African celestial connection. This sprawling medieval city, built between the 11th and 15th centuries, isn't just an architectural marvel, it's a stone compass aligned to the heavens. The conical tower at its heart casts shadows that mark solstices, while certain passageways frame the rising of specific stars during harvest seasons. Most striking is the eastern enclosure, where a narrow window perfectly captures the first light of the helical rising of Canopus, the second brightest star in the night sky. To the builders, this wasn't just decoration. It was a celestial clock synchronizing rituals and agriculture with cosmic rhythms. What ties these traditions together is their reverence for the sky as a living text. For the Dogon, Sirius wasn't just a point of light. It was the home of the Namo, amphibious beings who brought wisdom to humanity. In Zimbabwe, stars weren't distant fires but ancestors guiding the living. This fusion of myth and observation reveals a profound truth. Across Africa, astronomy was never just about prediction or navigation. It was a dialogue between Earth and sky, past and present, the visible and the unseen. Modern astrophysicists might map galaxies with equations, But these ancient scholars mapped them with stories, turning the cosmos into a tapestry of meaning as vast as the continent itself. The real mystery isn't just how they knew what they knew, it's why we ever assumed they didn't. When colonial scholars first recorded Dogon traditions, some dismissed them as lucky guesses or outside influence. But that skepticism says more about us than them. Maybe the greater lesson lies in recognizing that curiosity and genius aren't bound by technology or era. Whether etched in stone across Zimbabwe or woven into oral epics in Mali, these African astronomies challenge us to widen our gaze, to see the night sky not just through lenses, but through the eyes of those who studied it long before telescopes turned wonder into data. Perched high on a windswept plateau in northwest Iran, the Maraghe Observatory wasn't just a building, it was a revolution in stone. Built in 1259 under the patronage of Hulagu Khan, grandson of Genghis, this sprawling complex housed instruments so precise they could track a planet's wobble across the sky with razor-thin accuracy. At its heart stood the mural quadrant, a colossal 60-foot arc embedded in the observatory's foundation, allowing astronomers to measure celestial positions down to fractions of a degree. But the real genius lay in the minds working there. Nasir al-Din al-Tusi, the observatory's director, didn't just collect data, he shattered ancient Greek assumptions about the cosmos. His Tusi couple, a groundbreaking mathematical model, solved a puzzle that had stumped astronomers for centuries: how to explain the looping retrograde motion of planets without resorting to clunky, Earth-centered systems. With elegant geometry, he demonstrated that circular motions could combine to produce straight-line movement, an idea so revolutionary it would later inspire Copernicus himself. What set Maraghe apart was its relentless fusion of cultures. Persian, Arab, Chinese, and even Greek astronomical traditions collided here, refined through endless debate and observation. Al-Tusi's team included Hindu mathematicians from India, Nestorian Christian scholars from Syria, and Mongol engineers who brought Chinese star maps. This intellectual melting pot produced the Ilkhanic tables, a celestial catalogue so accurate it remained in use for over 300 years. The tables didn't just list star positions. They accounted for atmospheric refraction, corrected for observational errors, and even predicted eclipses with unprecedented reliability. When European astronomers like Kepler later pored over these tables, they were unwittingly standing on the shoulders of Persian giants. The observatory's legacy extended far beyond its instruments. Al-Tusi's student, Qutb al-Din al-Shirazi, took the work further by proposing centuries before European scientists that light refracts when passing through different mediums, explaining why stars twinkle. Another Maraghe alumnus, Ibn al-Shatir, crafted planetary models so geometrically sophisticated that when historians compared them to Copernicus's diagrams in the 16th century, the similarities were startling. Both used identical mathematical devices to eliminate Ptolemy's awkward, equant point, proving that the same ideas had traveled from Persia to Poland along the Silk Road. Yet perhaps the most astonishing thing about Maraghe is how it transformed conquest into curiosity. Hulagu Khan had once been a destroyer, leveling Baghdad's libraries during the Mongol invasions. But under Al-Tusi's influence, he became a patron of science, funding not just the observatory but a library housing 400,000 volumes. In this remote corner of Persia, the spoils of war were reinvested as tools of discovery, proving that even in an age of empires and upheaval, the human hunger to understand the heavens could bridge civilizations. Today, as archaeologists sift through the observatory's ruins, they're not just uncovering ancient instruments, they're piecing together the moment when medieval astronomy pivoted from myth to mathematics, setting the stage for the universe as we know it. In the hushed halls of Japan's imperial court, where every rustle of silk and brushstroke carried weight, celestial events weren't just observed, they were woven into the fabric of power. The Nihon Shoki, completed in 720, reads like a cosmic drama where shooting stars and eclipses dictated the fate of emperors. When a fireball streaked across the night in 680, scribes didn't merely note it, they linked it to political upheaval, recording how the sovereign promptly pardoned prisoners to appease the heavens. This wasn't superstition, it was statecraft. The Chronicles' meticulous entries reveal a pattern. Comets foretold droughts, blood-red moons heralded rebellions, and every celestial anomaly demanded ritual response. What seems like myth to modern eyes was, for the court, a sophisticated early warning system, nature's way of signaling when to plant crops, when to delay battles, or when a ruler's virtue was being tested. Centuries later, as Japan's Edo period dawned, a new breed of scholar emerged, one who revered tradition but trusted mathematics more than omens. Enter Shibukawa Shunkai, the samurai-turned astronomer who exposed flaws in the ancient lunar calendar imported from China. Working under the shogun's patronage in 1684, he didn't just tweak calculations, he rebuilt the system from scratch. His Jokyo calendar corrected errors that had drifted for centuries, aligning lunar months with solar years so precisely that harvest festivals finally matched the ripening of rice. But here's what's fascinating: Shunkai didn't discard the past. He anchored his reforms in indigenous observations, using records from the Nihon Shoki to trace eclipse cycles back over 1,000 years. In his hands, imperial superstitions became data points, proof that tradition and innovation could orbit the same truth. The real magic of Japan's celestial chronicles lies in their duality. Court diarists saw the sky as a mirror of human affairs, while Edo scholars like Shunkai treated it as a clockwork puzzle. Yet both approaches shared an unshakable conviction that the heavens spoke if only one knew how to listen. When a meteor shower lit up Kyoto's skies in 1730, officials consulted both astrologers and astronomers, one interpreting divine displeasure, the other calculating orbital debris. This cultural dance between reverence and reason birthed unique hybrids like Tenman-Gata, star charts that blended constellation myths with precise positional grids. Even today, traces of this dual legacy endure. Modern researchers still scour the Nihon Shoki for records of supernova, while Tokyo's National Museum preserves Shunkai's brass sextants, tools that once measured not just angles, but the delicate balance between sky and society. Perhaps the most poignant example sits in Osaka Castle's archives, a 17th century scroll depicting the Great Comet of 1680. Brushstrokes capture its fiery tail sweeping over cherry blossoms, while meticulous notes alongside document its coordinates and brightness. It's a snapshot of a moment when Japan's celestial observers stood at the crossroads, one eye on ancestral traditions, the other on a future where stars were no longer messages, but mysteries waiting to be solved. Across the vast deserts and rainforests of Australia, where GPS signals fade and modern maps go blank, Aboriginal peoples have navigated for millennia using something far more profound: songlines. These aren't just melodies, they're living maps woven into the very fabric of the land and sky. Picture a traveler walking through the outback at night, singing verses that describe the position of the Southern Cross overhead, the curve of the Milky Way beneath it, and the way certain stars dip towards specific rock formations or waterholes. Each phrase, each rhythm isn't just poetry, it's a coordinate, a turn-by-turn guide across hundreds of miles, passed down through generations without a single written word. At the heart of this system lies the Emu in the sky, a constellation unlike any in Western astronomy. While we see dark patches between stars as empty space, Aboriginal astronomers saw shapes in the cosmic dust, a celestial emu whose posture changes with the seasons. When its neck stretches high in the sky during April, it signals the time to gather emu eggs. When it appears to sit low in October, it's a warning that the eggs have hatched and hunting season has ended. This isn't just stargazing, it's an ecological calendar etched in the night, linking celestial patterns to the rhythms of the earth. The genius of songlines lies in their multidimensionality. A single song might describe a mountain silhouette against the horizon, the star that rises directly above it, and the ancestral story that binds them together. The Yolngu people of Arnhem Land, for example, sing of Barnumber, the morning star, as she pulls a rope of light behind her, a poetic description of Venus's pre-dawn glow that also serves as a navigational marker for fishermen timing their trips with the tides. These songs collapse distance and time, turning a journey across land into a journey through story, where every landmark and star holds layers of meaning. What's astonishing is how accurate these oral maps remain today. Researchers comparing songlines to modern topographic maps have found they often trace the most efficient routes between water sources, sometimes across featureless terrain. The stars act as waypoints, but the songs also encode subtle environmental cues, the smell of certain plants, the sound of wind through particular rock formations, creating a holistic navigation system that science is only beginning to fully appreciate. This tradition refuses to separate knowledge from culture, astronomy from art, or navigation from spirituality. When a Wardaman elder explains that the falling star Arcturus brings the monsoon rains, he's not just forecasting weather, he's recounting a creation story where the star being spills water from the sky. The songlines remind us that for much of human history, the universe wasn't something to observe from a distance. It was a conversation, a kinship, a story still being sung. And in the flickering campfires of the outback, where the emu's shadow stretches across the dust, that story continues, as alive now as it was 40,000 years ago. For the Aztecs, a solar eclipse wasn't just an astronomical event, it was a cosmic battle playing out before their eyes. When the sun vanished without warning, they believed the fearsome Tzitzimime, star demons lurking at the edges of the universe, had launched an attack to devour the sun god Tanatia. The Borgia Codex, a vivid pre-Columbian manuscript, captures this terror in stark imagery, skeletal deities descending from the sky, their clawed hands reaching for the darkened sun while priests below perform frantic bloodletting rituals to strengthen the weakened deity. These weren't mere illustrations, they were survival guides for a world where the universe itself seemed on the brink of collapse. What's remarkable is how the Aztecs turned that fear into precision. Their 52-year calendar cycle, known as the Zumulpili or binding of years, wasn't just a timekeeping device, it was a cosmic reset button. By interweaving the 365-day solar year with their 260-day sacred calendar, they created a system where eclipses could be anticipated, if not perfectly predicted. Every 52 years, when both calendars realigned, they extinguished all fires across the empire, symbolizing the potential end of the world. On a mountaintop outside Tenochtitlan, priests would watch the Pleiades star cluster. If it passed overhead at midnight, it signaled the gods had granted another cycle of existence. New fire was then kindled in a sacrificed captive's chest, and torchbearers carried the flames to relight every hearth in the empire. This ritual wasn't just ceremony, it was a profound acknowledgement of humanity's fragile place in the cosmos. The Florentine Codex, compiled after the Spanish conquest, reveals even deeper layers of their eclipse lore. Certain dates in the Tonalpohualli, the 260-day sacred calendar, were considered eclipse-prone, with ominous names like Oslotl, jaguar, or Kotl, serpent. Priests cross-referenced these dates with solar observations, creating a crude but effective early warning system. When an eclipse threatened, markets closed and people barricaded indoors, banging pots to scare away the demons. Pregnant women hid in granaries, believing the Tzitsamim targeted unborn children. These responses show how deeply celestial events were woven into the social fabric, not as distant curiosities, but as immediate, life-altering forces. Yet beneath the mythology lay startling astronomical insights. Recent studies of the Borgia Codex suggest its eclipse imagery corresponds to actual events. One page depicts a solar eclipse with a crescent-shaped corona, a detail only visible during annular eclipses, where the moon doesn't fully cover the sun. Another shows Venus near the eclipsed sun, a rare alignment that would have been observable only during specific celestial configurations. These weren't random artistic choices, they were records preserved in the language of myth. The Aztec legacy challenges our assumptions about primitive astronomy. Without telescopes or written equations, they built a system where terror and trigonometry coexisted. Their priests may have seen eclipses as divine battles, but their calendars prove they also recognized patterns, a reminder that wonder and calculation aren't opposites, but partners in humanity's timeless dance with the stars. Long before telescopes pierced the night sky, India's Vedic scholars were mapping the cosmos with a blend of poetry and precision that still leaves astronomers in awe. The Rig Veda, composed over 3,000 years ago, doesn't just describe the sun as a celestial body, it paints him as a golden-armed god, riding a chariot pulled by 7 horses, each representing a day of the week. But beneath this vivid imagery lies a startlingly accurate observation. The text notes that the sun's path divides the year into northern and southern movements, hinting at an early understanding of solstices. This wasn't just mythology, it was the birth of a tradition where science and spirituality orbited the same truth. Fast forward to the Surya Siddhanta, a 5th century text that reads like an ancient astronomer's manual. Its calculations for planetary diameters and distances are off by mere percentages compared to modern measurements achieved without a single lens or metal instrument. The text describes Earth as a sphere, calculates the length of a solar year within minutes of today's value, and even accounts for gravitational pull, calling it the force that makes all things fall toward the center. How did they grasp such concepts centuries before Newton? The answer lies in their tools, yantras. These weren't just instruments, they were works of art. The massive sundial at Jaipur's Jantar Mantar, for instance, stands 90 feet tall, its curved surface marking time with shadows so precise they're accurate to within 2 seconds. Eclipses held special fascination. While medieval Europe trembled at these events, Vedic astronomers like Aryabhata calmly explained them in his Aryabhatiya, written in 499. He described the moon's darkening during a lunar eclipse as Earth's shadow, not a demon swallowing the moon, as many cultures believed. His calculations used a sophisticated system of trigonometry, correcting earlier errors with a humility rare for the era. "This rule is given for the benefit of others," he wrote, "who may come after me and improve upon it." What set Indian astronomy apart was its refusal to compartmentalize knowledge. Temples doubled as observatories, their carvings encoding celestial alignments. The Konark Sun Temple, shaped like a colossal chariot, has 12 pairs of stone wheels representing months, each spoke casting shadows that mark hours with uncanny accuracy. Even rituals held cosmic significance. The Agnicayana fire ceremony, lasting 12 days, mirrored the 12-year cycle of Jupiter, linking earthly rites to planetary rhythms. Today, as modern physicists revisit the Surya Siddhanta's equations or study Yantra's geometric perfection, they're not just uncovering ancient science, they're rediscovering a worldview where the universe wasn't a cold machine, but a living, breathing entity. The same text that calculated planetary orbits also spoke of sunlight as the food of the gods, reminding us that for these scholars, the stars were never just points of light, they were teachers, guides, and eternal companions in humanity's quest to understand the infinite. Rising like stone fingers from the highlands of northern Ethiopia, the towering stelae of Axum have puzzled historians for centuries. These massive obelisks, some reaching over 100 feet tall, aren't just monuments to forgotten kings. They might be a celestial map carved in granite. Look closely at their peculiar features: false doors, intricate carvings of multi-story windows, and precise notches along their edges. Some researchers believe these patterns mirror the constellations as they appeared over Axum 2,000 years ago, with certain notches aligning to stars like Sirius or Orion's belt during solstices. The tallest standing stela, known as the Great Stele, even bears a crescent moon and disk symbol at its peak, an ancient motif often linked to celestial worship across cultures. Whether these were astronomical markers, royal tombs, or both remains debated, but one thing is clear: the Axumites didn't just build upward, they built with their eyes on the heavens. This cosmic curiosity didn't end with the stelae. Centuries later, Ethiopian monks hunched over illuminated manuscripts like the Kebra Nagast, blending biblical narratives with meticulous records of comets and eclipses. One 15th century gospel housed in a monastery at Lake Tonna depicts a comet with a fiery tail streaking across a page of vellum, a likely reference to Halley's comet's appearance in 1456. What's striking is how these scribes wove celestial events into their theology without contradiction. A solar eclipse might be described as the sun mourning in sackcloth, echoing biblical prophecy while also noting the exact date and duration for future reference. This duality reveals a culture where faith and observation weren't rivals but partners in decoding the divine. The Book of Enoch, revered in Ethiopian Orthodoxy, takes this fusion even further. Its vivid descriptions of falling stars and wheels of fire have led some scholars to speculate these passages record actual meteor showers or auroras, filtered through spiritual metaphor. One section details the movements of the sun and moon with surprising numerical precision, dividing the year into 364 days, a figure that aligns closely with ancient solar calendars. For Ethiopian astronomers, the sky wasn't just a spectacle. It was scripture written in light, where every comet's path or eclipse's shadow carried layers of meaning, from the practical to the prophetic. Today, as archaeologists scan the Axum stelae with 3D lasers and theologians pore over fading manuscripts, we're rediscovering a tradition that refused to choose between science and spirituality. The same hands that carved star-aligned obelisks also penned psalms about the firmament, proving that wonder and calculation have always been two sides of humanity's cosmic coin. Whether etched in stone or inked on parchment, Ethiopia's celestial legacy reminds us that the night sky has never been just a void to fill with data. It's a mirror, reflecting our deepest questions back at us across the ages. High atop a stone stele in Seoul's ancient royal observatory, the Chinsang Yolcha Bunyajido gleams under the moonlight, not as mere decoration, but as a celestial masterpiece carved in granite. Created in 1395 under King Tejo's orders, this star chart isn't just a map, it's a time capsule of human ingenuity, plotting 1,467 stars with astonishing precision. But here's what makes it extraordinary. While based on Chinese models, Korean astronomers didn't simply copy, they corrected. Centuries of observations from the Goryeo dynasty were distilled into this single slab, adjusting star positions to account for changes in Earth's axial tilt over time. The result, a chart so accurate that modern astronomers have identified at least 283 constellations still recognizable today, their patterns etched in stone like a frozen night sky. At the heart of this achievement stood scholars like Jang Yong-sil, a former slave-turned genius whose inventions transformed Korean astronomy. His water-powered armillary sphere, the Hanchanui, didn't just track stars, it sang. As celestial bodies moved, the device's intricate gears triggered small metal balls to drop into brass bowls, creating chimes that marked the hours with melodic precision. Imagine court astronomers in the Joseon dynasty, listening to the music of the spheres while recording planetary movements for royal calendars. These weren't just scientific instruments, they were bridges between heaven and earth, turning cosmic rhythms into something tangible, even beautiful. The practical applications were just as revolutionary. Korea's agrarian society depended on precise celestial knowledge to time rice planting and monsoon preparations. The Chiljeongsan, a 15th-century computational system, used the star charts data to predict solar and lunar eclipses years in advance, a matter of national security when celestial omens could destabilize kingdoms. During the reign of King Sejong, observatory officials would present annual reports correlating celestial events with crop yields, proving that astronomy wasn't abstract science but the backbone of survival. Yet the Cheonsang Yolcha Bunerjido reveals something deeper about Korean cosmology. Unlike Western star charts that isolated constellations, this map wove them into a grid of 365 small circles, one for each day of the year, linking stars to seasonal cycles. The Milky Way arches across the stone like a celestial river, mirroring Korea's real-life waterways that guided travelers. This wasn't just navigation, it was philosophy in stone, a reminder that humanity's place in the cosmos mirrored the balance of nature on Earth. Today, as researchers scan the chart with 3D imaging, they've discovered subtle grooves marking supernova witnessed by Goryeo astronomers, stellar explosions so bright they were visible in daylight. These faint etchings, overlooked for centuries, now help modern astrophysicists date cosmic events. The stone's endurance is poetic. Where paper burns and ink fades, the stars of Joseon still shine, silent witnesses to a civilization that saw the heavens not as distant lights, but as partners in the dance of life. 21st century sailors might rely on GPS satellites and digital charts, but the ancient Polynesians crossed thousands of miles of open ocean with nothing but the stars as their guide, and their precision would put modern navigators to shame. At the heart of this mastery lay the star compass, a mental map so precise it functioned like a celestial GPS. Unlike Western compasses that point north, Polynesian navigators like the legendary Maupiailug divided the horizon into 32 directional houses, each named for the star that rose or set there. The rising point of Altair marked one bearing, the Southern Cross another. But here's what's truly astonishing. These weren't just static markers. Navigators memorized how each star's position shifted with the seasons, adjusting their mental maps in real time as they sailed. A star that rose due east in June might angle northeast by December, and they knew every degree of that drift by heart. Maupiailug's 1976 voyage from Hawaii to Tahiti, a journey of 2,500 miles without instruments, revealed the system's brilliance. Without charts or a compass, he relied on the star compass, wave patterns, and the flight paths of seabirds. When clouds obscured the stars, he read the ocean itself. Swells refracting around distant islands created subtle interference patterns in the waves, detectable only to a trained hand trailing in the water. The color of the clouds, the taste of the wind, even the types of driftwood floating by, all were data points in a living navigation system honed over generations. What set the star compass apart was its seamless fusion of observation and intuition. Western navigation tends to separate the measurable from the experiential, but Polynesian wayfinding embraced both. Navigators didn't just calculate positions, they felt them. They spoke of T-Lapa, underwater lightning, a phenomenon where bioluminescent streaks in the ocean pointed toward unseen islands like underwater arrows. Modern science still can't fully explain it, but Mao's students swear by its accuracy. This knowledge wasn't written down. It lived in chants, dances, and the rhythmic cadence of oral teachings. A master navigator might spend decades memorizing star paths, wave signatures, and the stories that encoded them. The loss of this tradition after European contact nearly erased it entirely, until Mao, one of the last living masters, broke centuries of secrecy to revive it. Today, his students sail the Pacific using these ancient methods, proving that the star compass isn't just history. It's a living testament to the human mind's ability to map infinity, one star at a time. Deep in the peat bogs of eastern France, a corroded bronze tablet lay hidden for centuries until a farmer's plow struck metal in 1897. The Coligny calendar, as it's now known, isn't just a relic. It's a labyrinth of celestial mathematics etched by Gaulish hands 2,000 years ago. Imagine priests in sacred groves tracing their fingers along its grid of meticulously punched holes, each marking the waxing and waning of lunar months interwoven with solar cycles. This 5-foot-long bronze puzzle doesn't just track time, it reconciles it, balancing 29 and 30-day lunar months into a grand 19-year pattern that keeps moon phases aligned with the seasons. The precision is staggering. Every 62 months, an extra month is inserted to correct the drift, a system so refined it rivals the accuracy of later Roman calendars. But the true magic lies beyond bronze. For the Celts, time wasn't an abstract grid. It was a living tapestry where trees whispered cosmic secrets. Their sacred oak groves doubled as observatories, with particular trees aligned to mark solstice sunrises. The mythical Celtic tree calendar didn't just assign months to different species. It mapped constellations onto Earth, linking the heavens to rooted wisdom. The birch, associated with new beginnings, mirrored stars that appeared at winter's end. The oak, symbol of strength, corresponded to summer solstice constellations when its wood fueled midsummer bonfires. Even the alphabet held celestial ties. Each letter in the Ogham script represented a tree and its corresponding star pattern, turning writing into a celestial language. This fusion of arboreal and astronomical wisdom reveals a profound worldview. Where modern calendars separate nature from timekeeping, the Celts saw them as one. The Coligny calendar's intricate notations include symbols for auspicious and inauspicious days, phases where the moon's position relative to certain constellations influenced harvests or battles. A full moon rising near the constellation they called the Silver Branch might signal ideal timing for planting, while an eclipse during the Alder month could warn of coming strife. These weren't superstitions, they were observations honed over generations, recognizing patterns between celestial events and ecological shifts. What makes the Celtic system extraordinary is its resilience. Even as Rome imposed its Julian calendar, fragments of this sky-rooted timekeeping survived in folklore. The Irish tree months persisted in poetry, and the Welsh Battle of the Trees saga preserved constellation lore disguised as myth. Modern dendrochronologists, scientists who study tree rings, have even found evidence that certain sacred oaks were tended for centuries, their growth patterns subtly reflecting solar cycles like living almanacs. The Coligny calendar now sits in a Lyon museum, its bronze surface still whispering of a time when humanity didn't just observe the cosmos, they conversed with it through the rustling leaves of sacred groves and the silent dance of stars overhead. In its carefully spaced holes and cryptic notations, we glimpse a philosophy where time wasn't counted, but cultivated, like the slow growth of an oak reaching toward the same sky its ancestors once mapped. In the hushed scriptoriums of Constantinople, where candlelight flickered over parchment thick with holy ink, Byzantine scribes like Michael Glykas chronicled eclipses with a quivering hand, not as mere celestial events, but as strokes of divine judgment. When the sun vanished over the Bosporus in 1178, Glykas didn't just note the darkness, he described how the very air thickened with dread, recording how Emperor Manuel I rushed to donate gold to churches, fearing God's wrath. These accounts, preserved in manuscripts like the Annals, reveal a world where science and scripture bled together. A solar eclipse wasn't just the moon's shadow, it was a celestial rebuke, a moment when emperors cancelled wars and cities fasted in collective penance. Yet beneath the terror lay meticulous observation. Glykas's descriptions of the eclipse's duration, as long as a man might recite 50 psalms, later helped modern astronomers pinpoint the exact date and path of totality, proving even medieval fear could yield precise data. Enter Leo the mathematician, a 9th-century polymath who saw those same eclipses through a different lens. While monks crossed themselves, Leo refined the astrolabe, a handheld marvel of brass and calculation that could predict eclipses years in advance. His workshop in Constantinople's Magnaura Palace became a beacon of reason, where gears and dials replaced divine omens. One surviving manuscript shows his notes correcting Ptolemy's eclipse tables, adjusting for Constantinople's latitude with clinical precision. Leo didn't deny God's hand in the heavens, he simply believed it moved by mathematical laws. His students whispered that he'd engineered a mechanical throne for the emperor that roared with artificial thunder during audiences, a blend of theater and engineering that epitomized Byzantium's duality. What makes these records extraordinary is their layered legacy. The same eclipse that sent Glykas scrambling for his prayer beads was logged in Leo's ledgers as a predictable alignment. Byzantine chronicles often sandwiched astronomical calculations between accounts of plagues and palace intrigues, as if the cosmos were just another player in imperial politics. When a blood-red lunar eclipse coincided with Emperor Romano's Roman IV defeat at Manzikert in 1071, historians didn't just call it bad luck, they analyzed the moon's hue through Aristotelian meteorology, debating whether atmospheric dust from distant battles had tinted its light. The Byzantines' greatest contribution wasn't just their observations, but their preservation. As the Library of Alexandria crumbled, Constantinople's scribes copied and annotated Greek astronomical texts, safeguarding Ptolemy's Almagest through centuries when Europe forgot its own scientific heritage. Their eclipse records, spanning nearly a millennium, now help NASA researchers measure historical changes in Earth's rotation. In the end, Byzantium's scribes and scientists remind us that wonder and calculation aren't opposites, they're twin flames, each illuminating the heavens in its own way. High in the Himalayas, where thin air makes stars pulse like living things, Tibetan monks didn't just track celestial movements, they prescribed them. Picture a physician in the halls of Sera Monastery, unrolling a bark paper calendar marked with intricate grids. Each day isn't just a date, it's a nexus of cosmic influences where the moon's phase dictates which valley to harvest medicinal roots, and the position of Jupiter determines the optimal time to administer a fever remedy. This is Tibetan astrological medicine, a system so precise it calculates the best moment to pick a single flower based on the angle of sunlight during specific lunar mansions. The White Beryl, a 17th century treatise, doesn't just list herbs, it maps them to constellations, asserting that aconite gathered when the Pleiades rise gains potency, while gentian collected under a waning moon eases digestive fires. What sets this tradition apart is its refusal to separate astronomy from anatomy. Tibetan medical thankas, those vivid scrolls depicting the human body, often include celestial diagrams overlaying organs with planetary influences. The heart corresponds to the sun, the lungs to Mercury, and the liver to Jupiter, creating a microcosm where bodily rhythms mirror cosmic ones. A lunar eclipse wasn't merely an astronomical event. It was a warning to avoid bloodletting therapies, as the four medical tantras taught that gravitational shifts during eclipses disrupted bodily fluids. Even pulse diagnosis followed celestial logic. Physicians checked radial pulses at dawn, believing the rising sun's energy made vascular rhythms most discernible. The real genius lies in the calendar systems themselves. The Tsuapu calendar, still used today, interweaves lunar cycles with solar corrections in a 60-year Jupiter cycle. Each year bears one of 12 animal signs and 5 elemental attributes: wood, fire, earth, metal, water, creating a matrix of 60 unique combinations. This wasn't just folklore, it dictated medical practice. A fire horse year might see treatments emphasizing cooling herbs like sandalwood, while earth ox years called for warming therapies with ginger or saffron. Monastic astronomers adjusted these calendars annually, accounting for leap months with a system so accurate it diverged from modern calculations by mere hours over centuries. Today, modern researchers are verifying what Tibetan physicians observed empirically. Studies at Lhasa University reveal that certain alkaloids in high-altitude plants do fluctuate with lunar phases, while circadian biologists note how gravitational shifts during eclipses subtly affect cerebrospinal fluid flow. The Men Tsikong, Tibet's traditional medical institute, still trains physicians to consult planetary positions when compounding medicines, not out of superstition, but because 1,000 years of observational data suggests these correlations matter. In a world rushing toward AI diagnostics, this ancient practice whispers a radical truth. Sometimes the best medicine comes not from a lab, but from remembering our place in the living cosmos. Perched atop a hill overlooking the bustling streets of 16th century Istanbul, Taki al-Din's observatory was a marvel of its age, a glittering complex of domes and precision instruments that rivaled even Tycho Brahe's famed Uraniborg. Built in 1577 under Sultan Murad Roman III patronage, this short-lived institution represented the pinnacle of Islamic astronomy's golden age. Its massive brass quadrant, spanning over 6 feet, could track celestial movements with razor-thin accuracy, while its mechanical clocks kept time to within seconds, a feat unmatched in Europe at the time. Yet what truly set Taki al-Din apart wasn't just his tools, but his relentless pursuit of comets. When a brilliant comet streaked across the sky in 1577, he didn't just record its path, he challenged Aristotle's ancient claim that comets were atmospheric phenomena. His meticulous notes, preserved in the instruments of the observatory, proved comets moved beyond the moon's orbit, laying groundwork for Kepler's later breakthroughs. The observatory's legacy shines brightest in its star catalogues. While Tycho Brahe famously resisted the heliocentric model, Taki al-Din's team quietly compiled data that would have made Copernicus nod in approval. Their onboard Pearl catalog charted over 1,000 stars with positional errors smaller than the width of a fingernail held at arm's length. One particularly stunning diagram depicts the supernova of 1572, the same new star Tycho observed, but with Arabic annotations noting its fading brightness over months, a detail European records missed. This wasn't just competition between East and West. It was the unfolding of a global scientific conversation, where observations from Istanbul, Prague, and Damascus collectively chipped away at outdated cosmic models. Yet the observatory's brilliance burned briefly. Within a decade, conservative clerics convinced the Sultan that prying into heaven's secrets invited divine wrath. The instruments were dismantled, the buildings raised a cautionary tale about knowledge caught in political crosscurrents. But Taqi al-Din's work survived in unexpected ways. His treatise on mechanical clocks influenced Ottoman timekeeping for centuries, and his comet studies resurfaced in 17th century Persian texts that eventually reached European scholars. Today, archaeologists sifting through the observatory's original site still find fragments of astrolabes bearing his distinctive engraving style, their delicate markings whispering of a moment when Istanbul's skyline hosted one of history's most audacious attempts to measure the infinite. What makes this story poignant is its unfinished potential. Had the observatory endured, its combination of cutting-edge instruments and Taqi al-Din's innovative math, he pioneered the use of decimal fractions in astronomy decades before Europe might have accelerated our cosmic understanding. Instead, it stands as a reminder that scientific progress isn't inevitable. It's fragile, shaped by the clash of curiosity and dogma, and sometimes the most brilliant chapters are those cut tragically short. Yet, even in its fragmentary legacy, the observatory proves how borders melt under the shared sky, where a comet's tail belongs neither to East nor West, but to humanity's collective hunger to understand the night. In the frozen silence of the Arctic night, where temperatures plunge so low that breath crystallizes in the air, the Inuit didn't just survive. They thrived by turning the sky into a storybook and a survival guide. Their legends paint the auroras not as abstract light shows, but as the joyous spirits of ancestors playing a celestial ball game, their laughter crackling across the heavens in waves of green and pink. But beneath this poetic imagery lay razor-sharp practicality. Elders taught that whistling at the lights could summon them closer, a warning disguised as folklore, since the eerie sounds often preceded brutal storms. This duality, myth as meteorology, reveals a culture that saw no divide between wonder and utility. The stars, too, were more than pretty lights. Inuit navigators memorized the Kilak, their star compass, where constellations like the Pleiades, Nanajuk, and Orion's belt Sukuliasujutuk acted as seasonal markers. During winter hunts on shifting sea ice, hunters watched for the three stars in a straight path, Orion's belt, to orient themselves when landmarks vanished in endless white. But the real genius lay in their lunar knowledge. The moon's phases dictated seal hunting strategies. A full moon's bright glare made it harder to approach breathing holes, while darker nights offered cover. These weren't casual observations, they were life or death calculations passed down through throat singing and bone carvings. One particularly ingenious trick involved using the sun's refraction. On bitter winter days when the sun barely grazed the horizon, Inuit travelers would note how its distorted, flattened shape indicated temperature layers in the atmosphere, a natural weather forecast predicting coming storms. Similarly, the position of the moon's halo could signal wind direction, with ice crystals acting as a celestial wind vane. What's astonishing is how these traditions persist. Modern researchers working with Inuit elders have identified star lore that accurately describes Jupiter's moons observed not with telescopes, but by noting the planet's subtle brightness fluctuations over generations. The Inuit's celestial knowledge wasn't just about survival. It was a profound dialogue with the cosmos, where every shimmer of light carried layers of meaning, from the practical to the sacred. Their legacy reminds us that the harshest environments often breed the most intimate relationships with the sky, not as distant spectacle, but as teacher, ally, and living story. From the moment our ancestors first traced the outline of a supernova on a cave wall to the intricate star charts pressed into Babylonian clay, humanity has never stopped reaching for the heavens. What unites these ancient chroniclers, whether they painted eclipses in ochre, aligned megaliths to solstices, or sang navigational paths across the Pacific, isn't just curiosity. It's the profound need to transform wonder into legacy, to say to the future, we were here and we saw this too. Take those handprints stenciled beside star symbols in France's Lascaux caves. They're more than art, they're signatures, a Paleolithic astronomer saying, "This is my witness." Fast forward to Tycho Brahe's notebooks in the 16th century, filled with meticulous comet sketches, and you realize nothing has changed. We still chase the same impulse to freeze the ephemeral, to make the cosmic personal. The difference, today we use smartphones instead of charcoal, but the awe remains identical. What's staggering is how these ancient records still serve science. When researchers matched Chinese descriptions of a guest star in 1054 to the Crab Nebula's expansion rate, or used Babylonian eclipse tablets to measure Earth's slowing rotation, they proved these weren't just myths, they were data. The Maya's Venus tables carved into temple walls predict the planet's cycles more accurately than medieval European models. The Dogon's knowledge of Sirius B, passed orally for generations, rivals telescopic discoveries. These weren't primitive guesses, they were the result of lifetimes of patient observation, honed by cultures that saw the sky as both classroom and cathedral. Yet the true magic lies beyond utility. When Polynesian navigators chanted the rising points of stars, or Inca priests knotted eclipse cycles into quippers, they weren't just recording, they were relating. Their methods reveal a truth modern science sometimes forgets. Understanding the cosmos isn't just about measurement, it's about meaning. The Norse watching auroras dance and seeing Valkyries weren't wrong. They were layering human experience onto physics, reminding us that the universe isn't just equations, it's stories. So as you look up tonight, remember, you're part of that unbroken conversation. The same stars that guided Maori sailors to New Zealand still anchor our GPS satellites. The same eclipses that terrified Aztec kings now draw crowds with eclipse glasses. The methods change, but the marvel doesn't. Whether it's the Inca's knotted cords or China's silk star maps, each tradition whispers the same thing across time. Look. Remember, pass it on. Now it's your turn. Which ancient chroniclers speak to you? The monks who inked comets into psalters, the builders who coded solstices into stone. Drop your pick in the comments and keep the dialogue with the cosmos alive. Don't forget to hit subscribe. We've got millennia more wonders to explore together.